there was changes in the plan, and we don't have a chair for this session. So I decided that I can also chair it. And so without further ado, I want to introduce the next speaker. It gives me great personal pleasure. I've been following his work for many, many years. So Omer Reingold is going to tell us about on the interplay of accuracy and fairness in computational healthcare.
Do you want me to do the time?
Yes. Thank you very much for the kind introduction. Okay, so one thing I need to clarify immediately is that I'm not a physician, I'm not a researcher in healthcare, and whenever you're kind of in these multidisciplinary settings, you always feel a little bit like a fraud. But we're here to be brave, so we'll do that. Everything I know about healthcare is from Noah and Noam and Ran, that for some reason like to play with me, and from meetings like that. So there are two approaches. One approach, and one thing I learned is that I should have become a physician, because somehow the moment you put a stethoscope and you look much better. I don't know. So one option is just to put healthcare in the title and then to give the usual generic talk about fairness. It's not completely different than what I'm doing, but I'll try to think about what I think could be interesting from the perspective of healthcare, and even there are a couple of examples from healthcare. But I'm going to keep it in a very, very abstract manner. So we won't see graphs of A, because I'm a theoretician, and B, because I want to talk about the principles. Okay, so that's the introduction. So decisions. Turns out that every day we're making 35,000 decisions. And with all of these decisions, it's really natural that we want to rely more and more on algorithms. And we are relying more and more on algorithms for small decisions and also for big decisions. So one decision I had to deal with is what number to put there. And I used my favorite LLM that told me that we make 35,000 decisions. So this is one decision that I saved using algorithms. And I cannot motivate AI in healthcare better than Ran already did in the first day. But to summarize, either we adopt AI in healthcare or we're all going to die. I'm paraphrasing just a little bit. I also cannot motivate fairness in computational healthcare better than Noah did. And it was interesting. I really loved it at some point. During the presentation, somebody asked, okay, but what do you mean by fairness, or what is fairness? And this is exactly the kind of question that we're going to talk about. And in fact, this is exactly the kind of question that my field, which is the theory of computing, kind of focus on when we're talking about fairness. So what is this fairness that we're talking about? What I can try to offer is some insights about fairness from the perspective of a theoretician. Okay. So I want to emphasize that it's not only about fairness. The moment that algorithms are so central in our life, a lot of the kind of public debates or societal questions revolve around computation. So we started this meeting with privacy, and privacy is one of these areas that has been studied the most in terms of, from a theoretical perspective, and we have lots of tools, and we heard a lot from Katrina. Fairness, that's what we're going to talk about today, and many, many other topics. Most of those are not related specifically to healthcare, but there are also other questions that relate to healthcare when you're doing AI. It's not only privacy and fairness. The moment we have this other creature in this equation, which is an algorithm, we really need to deal with what does it mean. Okay, but what is this algorithmic fairness? So the concern that we want to deal with is that algorithms will discriminate against groups or individuals on a basis that is protected by law or policy or ethics. For example, we have this in law, we have this notion of protected features, protected groups, based on attributes like gender, race, ethnicity, and so on. And we want to prevent discrimination on this basis. And this is, when we started to work on it, which was 2010 roughly, it was kind of mostly a theoretical concern, but since then we've seen plenty of examples. We'll also talk about examples from healthcare. And beyond those examples, there is a change in public perceptions of algorithms. The perception is not only, okay, here are those geniuses that are going to revolutionize the world, but also these are the evil geniuses that are going to destruct the world. And if we want, for example, in healthcare, that people would agree to the incorporation of algorithms within something so sensitive as healthcare, we need to do something about this perception and also this reality where discrimination does exist. By the way, please ask me questions. Nothing is too simple. I owe you lots of simple, so if you don't ask very, very basic questions, I'll feel that we don't have, yes, please, thank you.
Yeah, so we're defining algorithmic fairness and perceptions and other beliefs about algorithms and fairness. Are you going to get around, or do you know of, or is it really related to like the Donald Knuth's general guidelines of an algorithm has an upper bound and a lower bound? Is fairness tied to having upper bounds and lower bounds?
I'm not sure what do you mean by upper bounds and lower bounds.
Well, if it doesn't have one of those two, it doesn't have like two of those bounds, it's not an algorithm. So I'm sort of asking, like, do people have perceptions about algorithms and fairness that are actually tied to real algorithms or to things that people assume are algorithms?
I'm not 100%. I'll try to answer, but correct me if I don't get it right. So I didn't actually talk about what are algorithms, and perhaps that's a good place to start. So algorithms are kind of procedures for making a decision in a systematic way. And we've been doing algorithms, all of us are kind of computers. We've been doing algorithms all the time, both explicitly and implicitly. Whenever we do long addition, we are running an algorithm. But whenever we're also recognizing a person that we know, and it's also an algorithm. So an algorithm has lots of different properties. So we can talk about the efficiency of an algorithm, the correctness of the algorithm, what does the algorithm does it correctly all the time. So from our perspective, fairness is one more property of algorithms that we need to deal with. And it's not only a perception of discrimination, there has been real discrimination in systems. So for example, let's give one of the famous examples, the gender shade example, where kind of facial recognition software that was the best at the time did much better on men than women, and much better on lighter skinned people than darker skinned people, and it also composed. So it was almost perfect for white men and very bad for dark skinned women. Okay, so that's the spiel, but I don't know if I answered. Or we can talk about it offline. Okay, good. I'll just say that it's natural that we will worry about that, because when people are making decisions, we do have laws and regulations that prevent them from discrimination. The fact that we are using algorithms doesn't mean that now we don't need to worry about it anymore. If algorithms are now making decisions or informing decisions, they need to be held at least to the same standards, if not more. Like we expect more from cars that are driving by themselves than from people. So definitely we need that. Okay, so what's the question that is probably on your mind after seeing that? The natural question is, what is fairness? So just saying, okay, fairness is not discriminating didn't solve much. Then what's discriminating, right? And I can use another word, perhaps talking about being impartial, but then what is impartial, and so on. So we can run around it all the time. And the answer is that I don't know. So this talk looks less and less appealing. I already said that I don't know anything or much about healthcare, and now I'm telling you that I don't know what fairness is. But in my protection, I think that nobody knows. And the reason is that fairness is not something to know, it is something to choose. So fairness is about values, and there are lots of different values, and you need to choose, what do you mean by that? It's just like I would ask you, okay, what is beauty? And okay, give me a very clear definition that an algorithm will identify, and this is beautiful and that is not. Fairness is similar to that, so it's in the eye of the beholder. And that's where my field, theory of computing, enters the picture. And what we've tried to do is to create a language of fairness. So we are not trying to tell you what fairness is. We're trying to provide a language of fairness that allows us then to debate about what fairness is, but to debate in a language that will allow us then to tell our algorithms to be fair. If we just debate at the level of philosophy, perhaps it will be more problematic. So what we do is give models, definitions, algorithm theorems, and with that we can express our views or human views about fairness. And in that we are following examples from other fields where it was very, very successful, cryptography, game theory, and more, where coming up with the right definitions really change areas. So what do we get from definition? It helps us bridge normative aspirations, like, okay, we want to be impartial with computational realities. We have something that we can really tell our algorithms to do. And it also allows us to represent new trade-offs, new things that we can do. Like in Katrina's talk about differential privacy, without definition it would have been hard to say, okay, let's do something in a differentially private way. And we'll see an example in this talk of something that's very hard to imagine we could have come up with without the right definitions. And those definitions had both practical and scientific impact, even beyond these notions of fairness. So that's kind of where my area, or essentially the philosophy of my area towards fairness. So let's be a bit more specific. We can't cover everything. I won't try to cover 15 years of research on machine learning fairness in one talk. I'm going to focus on two kinds of problems and one tension. So the problems are, first, classification. And there's lots of different problems of classification. So do you vaccinate or not? Give statins or not? Do a surgery or not? So these are Boolean classification, yes, not. We can choose one of a collection of different medical interventions. And classification can also be to a real valued thing. How much insulin I want you to use. Again, for simplicity, we're mostly going to talk about yes/no questions. The other thing is predictions. We'll talk about predictions even more than classifications. So for example, and we have lots of examples from healthcare, what is the 10-year risk of developing a major cardiovascular disease? So that's a prediction problem. I want to give you a probability, 4%, 7%. And the two are related. So for example, based on this prediction of the probability of a heart attack, I may decide to give you statins or not. But it's not connected in an automatic way. It's not like you take a predictor, and then the only way of using a predictor is to take everybody above some threshold. You can use predictors in different ways, which we can discuss. In healthcare, often what we really want to predict is not a particular probability. We want to predict a treatment effect. So not only would you have a heart attack in the next 10 years, but to what extent I'm reducing this probability by giving you statins. And much of what we're going to discuss is relevant for that as well. And there's lots of other, so when we'll talk about it today already as if we have a specific prediction problem in mind. For example, the probability of a heart attack in the next 10 years. But what we choose to predict is in itself an element of fairness. Yes?
I have a question. Sorry, I missed the 5 minutes, so maybe you said it, but
You missed the joke
okay.
that I'm very upset
so
about.
Actually, even more sorry about that. But when you say, at least all the examples that you show in the classification are things that are actions, to do or not to do, as opposed to when you say prediction, it's also in the kind of traditional ways classification did this person have or will that person have or won't have heart attack? So is the difference here action versus not action, or there's
that's a good point. I mean, classification doesn't need to be associated with an action. For example, I have an image and I classify it to an image of a cat, an image of a dog, an image of a car. But in many of the examples that we care about, this classification leads to an action. Prediction, the main difference in my mind is that prediction is really about trying to identify a distribution. So if it's yes, no, it's just a single probability distribution. And if I wanted to, in this image case, I would perhaps have a probability that this image is of a car, a cat, or a dog. So I want to talk about kind of probabilities versus classification, and the classification that I will care about has to do with action, because that's where, I mean, the moment an action happens, the moment the probability affects an action that affects individuals in major ways, that's where fairness becomes really critical. Thank you. Okay, so what we predict is very important. So yeah, how much we changed a probability of some medical event, but perhaps instead, as Noah talked about, how many years of life we're increasing. It's a different prediction altogether. In admission to universities, many of us are in universities, we can ask, okay, what's the probability a student will graduate in 4 years with GPA above 3.5? But we can also ask what's the probability that this person will be very successful in one way or another 10 years down the line. And you can try to optimize different things. So what you choose to optimize is part of a fairness choice. We shouldn't think about it as something obvious. And finally, there are many other domains. We may rank individuals, perhaps based on their probabilities, cluster individuals, and of course, on all of our minds, we have generative AI. And when I organized the workshop I organized a week ago, but a year before, I kind of invited 4 talks that were clearly going to be about generative AI, and then the 4 other talks were also about generative AI, because everybody cares about that. Since I want to talk about some of the very basic principles, I will not talk about it. Some of what we're talking about is relevant to generative AI, but generative AI brings many, many more considerations. And for those, research is still in kind of exploration stage. We don't have as strong definitions as we have in this sense of predictions, but happy to talk about it after. Okay, so that's the problem. Good. And now we have lots of, so fairness, right, I said there is no single definition of fairness. There are many, many definitions of fairness. So the question is to specify a definition of fairness is actually to specify the particular values, to specify what we care about. And what we care about can be on very different axes. And I'm going to focus here on the tension between equality of outcomes, treating everybody the same, at least with respect to groups, versus accuracy, being faithful to the data. And I think this is a tension that is especially interesting or important for healthcare applications. But there are other major kind of debates. For example, fairness to groups or individuals, which we'll also touch upon a bit, and which you can think about it as the tension between clinical versus actuarial approaches. And also kind of puts in the spotlight this idea of personalized medicine, which perhaps is never really personalized. Perhaps it's kind of associates you with the group, and it's personalized to a group that contains you, but it's never exactly per a particular individual. So it's a very interesting tension as well. Beyond that, many, I mean, this research talked about many things. So basing definitions of fairness on observational data versus causality, which exactly like in healthcare, we can do just one. We need both. Definitions of fairness in the moment, or what happens downstreams after we apply that. Fairness in isolation or through composition, which kind of brings me to think about drug interactions. When we analyze something and ask, okay, is this fair or not fair, and we think about this as being the only thing that happens, we may get one answer. But if we have examples where several things happen altogether, each one of them seems completely reasonable and fair, but together something very bad happens. Notions of interpretability, explainability, what do they mean? How are they fair or not? Strategic manipulations and malicious behaviors. We even talked in the last few days about not everybody doing right what you want them to do. Particular patients don't always do what you want them to do or hope they would do. And of course, a lot of emphasis on fairness in the data. Which features we care, what do we kind of measure? Are the data representing of different populations? Are we using the correct labeling? One example from healthcare, classic example of a failure, of fairness failure, comes from this example where the kind of the level of expenses of healthcare treatment was used as a proxy for the severity of a medical condition. And then populations that were kind of excluded mostly or from healthcare treatment naturally had spent less money on healthcare. So it turned out, for example, that black patients had to be much more sick to be considered sick by the models that you get when we use the wrong proxy. So all of these are very interesting, but that's not all of it can fit my talk. Okay. So fairness versus accuracy in healthcare. Yes?
Just to clarify the previous slide, would it be correct to assume that you think of fairness as a monotonic attribute, because fairness could also be non-monotonic?
No, I don't think about fairness as monotonic. In fact, one of the criticisms from some communities is about using the word fairness at all, which I don't accept because I think it's a bit extreme. But because, yeah, you can implement one fairness measure, it can cause harm in a different measure. So therefore,
or even in itself, right?
Sorry?
Or even in itself, as it accumulates.
So fairness for me is not, it's not a knob. And for every particular definition, perhaps there is a knob that can tell you, I want more fairness or less fairness under this notion. But the entire thing is kind of a landscape where you try to find the right position in this landscape. Yes?
So does that mean you don't expect fairness across a global landscape to actually converge at some point?
Yeah, I don't think that, yeah. In fact, I think that every interesting thing that we study, or no interesting thing that we study have one single definition. Even things that are technical, like if you talk about computer science, you ask what is efficient algorithms. There are many different notions of efficiency, and they have trade-offs. Perhaps in one you use more memory, in one you use more time. And so it's always about choice. And of course, efficiency is 1,000 times simpler than fairness. So yeah, fairness, the mantra that we've been saying for 15 years is fairness is a matter of societal norms and context. So in every context and every society we'll get a different meaning of, yeah, please.
Okay, so if we're using an algorithm that's expected to be fair, and we're leaving it up to Boolean satisfaction of some type, does that mean the complexity may result in it being undecidable as to whether or not we could actually decide if something's actually algorithmically fair?
So that's a very important question, and one reason for which efficiency and understanding, you can't, so kind of part of what we're trying to say is that you can't talk about fairness without talking about computational efficiency when you're thinking about decision making, and whether or not you're thinking about machines, because people cannot compute things that, they also have limited computation. So if we can show that a particular notion of fairness cannot be computed, then perhaps it's not the right notion in general, and it's kind of following the philosophical principle that ought implies can. You cannot come with an ethical demand, a demand to behave in a particular way, if behaving in this way is impossible. And what's impossible or not possible, what is possible or not possible depends on our understanding. So what you can decide and actually what you can decide efficiently. And this will come up in a particular definition we'll get to. Good. So I want to talk about fairness in healthcare. And I'm going to give an old example, which took attention, I don't know, a decade ago, about searches. You do a Google search, Google email search for a CEO, and this is what you get. Completely just pictures of men. And okay, so perhaps we're unhappy with that, but what would be a definition of fairness for us? So one option is to say, okay, there are not enough women CEOs in the world, but it's not zero. At least let's see the right fraction representing the world. And by the way, the classic example was about CEOs, but if we want to translate it to this meeting, we can search for physicians or nurses, and we'll see. And we can also translate it to generative AI and ask for a story about a CEO or a story about a nurse, and let's see what gender this CEO. So, sorry?
Or a criminal.
Or a criminal, yeah. And in generative AI, this issue of representativeness is even more complicated because, okay, you give me a story about a woman physician. Is this woman characterized in the same way in your stories about men physicians? Or is there a stereotypical presentations there? So it becomes more and more complicated, but even here it's complicated. So do we want to represent the ratio in the world? Perhaps we want to represent the ratio in the world that we would like to see. So perhaps we want like 50%. Or perhaps, kind of like Ruth Bader Ginsburg said, perhaps we want to overcompensate and to help push things in the direction of the world as we want. Which one is the right fairness? So these are notions of fairness that, I mean, perhaps that go from accuracy towards perhaps more equality or some societal demands. And this is domain dependent. The answer, what we want, will change in the domain. So it's different when you're thinking about university admission, where perhaps a little bit more equality, if the Supreme Court allows, is valuable. And perhaps different when we ask about loans, and perhaps we won't require the bank to give loans to people that are unable to return them just in the name of equality. But in healthcare, it seems that mostly equality of outcomes do not make a lot of sense. So saying here, I want to see exactly the same number of women CEOs and men CEOs makes sense, or could make sense, that could be argued for. It's values. Here, if I tell you that I require you to refer men at the same frequency to mammograms, I don't know what you'll tell me. I'm guessing you don't think it's a good idea. So perhaps we don't want equality of outcomes. And the same with, right, we won't send people to with the same frequency to art surgery between men and women if there are more, yeah, sorry, yeah.
Yeah, so it reminds me of something that I thought it was interesting. I don't know if it fits really with, but the first signs of heart attack are not the same with male and female.
Right.
And so working on the brain, every time I found something different between males and females, especially in France, I get, hundreds of, no, you should not say that males and females are different in the brain.
Right.
And in fact, it was very against the idea of equality. But now I think the feminist activists, they say, okay, we are maybe different, and you were looking only at males when you look at the heart attack aspect. So please take care of our difference, which is, I think, really a good move to say, okay, we need more fairness. I mean, I don't know if it's fairness, but that to discriminate is lead to more fairness. And I think it's a way of it's a positive, I think, progress of the society. I hope that it's going to be equity instead of equality.
Right. So let me put the next line. The next line is, which is exactly why I'm very thankful. Yes. So we don't want to send at the same level of to mammograms, but breast cancer is underdiagnosed in men. And there is a reason that I'm giving this example rather than the example of heart attacks for men and women, because, for good reasons. But there are two. There are differences, and there is, of course, the question of do we do the research? On which populations do we do the research? Who do we care for in intervention? So all of these questions are good. But the only thing is that, so perhaps equity rather than equality.
Mm-hmm. Yeah. That was my question.
Okay, perfect. Similar phenomenon in elderly patients, in patients with obesity. Some diseases are underdiagnosed in all of those. A friend told me that people that are overweight come with an ear infection, and the physician will tell them, oh, you need to lose weight. So So yeah, so kind of being viewed just with a particular perspective prevents diagnosis of diseases. On the other hand, again, some of the time, particular symptoms in elderly people are age-related and not, so it's not that we want equality. So now we're going to send older patients to test at the same frequency. But we should care about underdiagnosis. Yes?
I think there's an important, I think for all of these examples, there's a big difference, let's say in breast cancer example, between the prevalence of breast cancer in men and women. And so when we think about it's underdiagnosed in men, right away, at least the way you phrase it, I compare it here to how it is maybe less underdiagnosed in women. I don't know if it's underdiagnosed or not. But I think the fair comparison here would be to other conditions that are rare in men or women. And is it more underdiagnosed than other rare conditions in men?
That's a good question. But I'm just saying there is a particular notion of fairness that we'll see in a slide that would say, condition on having breast cancer, I want to diagnose it with the same probability for men and women.
So I guess I'm asking before even the next slide whether this is the, to me, I'll wait for your next slide.
For you, it's too optimistic.
It's not only that it's too optimistic. I don't view this as the fair comparison, but I'll wait for the, and because for me, these are two, imagine that these are two different diseases. They're not, maybe, I actually don't know. But one of them is a rare disease and the other one is a very common disease. And so a common disease is going to be diagnosed way better, like way less underdiagnosed than a rare disease.
Again, I won't have an answer to you even next slide or by the end because, as I said, it's all issues of values.
Yeah.
But I'll give you two different notions, one that follows this a bit more and one a different one. But let me represent what people that would argue for that, to say that these false positives and false negatives are a form of harm. And so you want harm to be spread the same among different populations. And yeah, one reason I'm using that, we don't often think about men as protected group, but if I use a different example from the other direction, it may be too sensitive. So I chose this example because it's convenient and less controversial. But yeah, I don't know what's the conclusion. In general, in all of those, I don't know what the conclusion. But certainly, I think the conclusion is not we want to send men at the same frequency for diagnosis. We want some notion of accuracy. Okay. So one reason I like this as an application area is that the connection is closer between fairness and accuracy. I'm going to speed up a little bit, although I love this discussion. And yeah, one last point. When we talked about privacy, and I think many times in healthcare we think about privacy as a price you need to pay. We want to do research. If we could just share all the data, but we need to deal with this annoying privacy, and for that reason, we're not doing as much good science as we could. Katrina tried to argue that actually insisting on privacy also is part of doing the right science, but mostly we think about privacy as a price we need to pay. Sometimes fairness is not a price. Sometimes it's consistent with what you want to do. Okay, so individual probabilities, take one. I'm going to kind of define our setting a little bit more. I'm going to speed up a little bit so I get to a particular punchline, but we'll see. Okay, so for this talk, we're going to focus on Boolean outcomes, will or won't have experienced a heart attack. By the way, these predictions could be in the present. So we're thinking about it as prediction, but we can say, okay, does this person have a breast cancer or not now, or a particular disease now, and we're talking about it as prediction. But we assume, we have a fiction, and we heard about it in the last talk, we take the fictional assumption that there is some distribution on patients and outcomes. This is a very strong assumption, but we make it all the time. and we'll kind of push against it a bit later. And then if we have this distribution, then there are also true probabilities. We have the Bayesian probability that tells me here is a patient. That's the probability of this patient having a heart attack in the next 10 years. So we have a specific probability. Of course, this is a fiction because every individual, right? I'm one person, I'm going to experience the next 10 years once, and either I'm going to have a heart attack or not. So what does it mean for me to have some probability, to have 4%, 5%, or whatever percentage? And of course, I didn't invent this question. It's the central, perhaps, foundational question, or one of the central foundational questions within statistics, debated for ever. And I'm going to give you, if I'll get to, a computational interpretation of the meaning of individual probabilities in a different perspective. But for now, let's assume that this P star exists. People have probabilities. There is something that nobody sees, but it's written on my forehead, which is the probability of. So even that we don't understand these probabilities, we're trying to approximate them. We're trying to learn models P that approximate this P star that I don't know exactly what it means. But that's the rules of the game. Okay. So now we want to say, okay, we wanted accuracy. Let's say we agree that we want accuracy in healthcare. But what does accuracy mean? So one thing is false positives, false negatives. We have errors. This is something we want to minimize. So for example, if I send a patient to a mammogram, they don't have breast cancer, this is a false, false positive, or it's hard, sometimes the positive and the negative get mixed, and vice versa. And a notion called equalized odds will ask that false positives and the false negatives are the same in a protected group S or at the general population T. So the probability we send men that we make false positives or false negatives for men and women are going to be the same, or any other protected group. So that's one notion. It's based on accuracy because we want the same level of accuracy for two populations, for S and for T. Here is another notion of fairness, of accuracy, which is calibration. So let's look at all the individuals whose features are X, such that, this should be P, not P star, such that my predictor P say on them 0.1. I want it to be the case that 10% of them is going to see the outcome that I'm talking about. 10% of them are going to have a heart attack in the next decade. What does it mean? It means that these probabilities, numbers that I give, I don't know what they mean for individuals, but at least over groups, they mean what they say. And this is pretty basic if we want to base decisions on it. I've been going with an umbrella all the time, this workshop, because the weather report says that it's going to rain. But let's say it says that it's going to rain with probability 5%. And I don't mind getting wet once in every 20 days. And if this is calibrated, then I can trust it. I can say, okay, I'm not taking an umbrella on days where it says 5% or less. It means that once in 20 days I'm going to get wet. That's okay for me. But it's only okay if the predictor that told me that is calibrated. If it's not calibrated, I shouldn't base decisions. It's not rational to base decisions on it. So can we get both? A very basic impossibility result shows that equalized odds and calibration are inconsistent. You cannot get them both unless some triviality happens. Now there is a star here because I defined two things in different worlds. One is a predictor and one is a classifier. But you can translate, you can talk about something like calibration for decisions, and you can talk about something like equalized odd for for predictors. And in both cases, either for decisions or predictors, the two things don't work together. And perhaps this confirms what you were worried about. We'll see it in a second, if the base rates are very different, then it's a very strong requirement to ask for equalized odds.
Yeah, just to clarify what I was worried about. Actually, both of these examples. If you have something which is more rare, or just a group that you have way less data on that group, then in order to get any type of fairness of this, both calibration and I think equalized odds, you essentially have to reduce the accuracy substantially for the group that you have a lot of data on, to make it fair. And then the question if that is fair. In my mind, it's not. But I can understand where someone would
So
say.
calibration, you don't actually need a lot of data. You can do it in a very, very simple way. You just say about everybody in the group
Just
a single
get
number. So
calibration,
just
right.
calibration is very, very easy. And it's kind of useless. And that's the reason we may, if I get to something more sophisticated in calibration. For equalized odds, I agree with you, but we should also say that the amount of data that you gather is part of the equation. Perhaps you need to gather more data.
Well, if something by definition is, if you have a disease 1 in a million and another disease in a different group 10%, then you'll have less data on the 1 in a million. I mean,
Yeah, but it doesn't mean that that accuracy should suffer. It's not complete. We have notions where accuracy, at least for calibration, doesn't suffer. Yes.
So please correct me if I'm misunderstanding, but I think part of what you're getting at, which I don't think disagrees with any of these, but is potentially relevant later, is that the task itself may be more difficult on different populations, and so it's maybe we should be asking not about the output performance, but on how close we are to the how good we are relative to the difficulty of the task.
yeah, and I think it's a question of the definition of fairness. To me, it's to be fair is to try hard on both, right? And so we have to try harder to get to the same result. Then
I completely agree with you. Apart from the fact that it's not a static setting. So sometimes, for example, if you gather one additional feature that's meaningful for one population then perhaps it becomes easy. So is it easy or hard? Sometimes depend on what we do. So sometimes it's hard to make predictions on a particular group. Why? Because we didn't collect the right features. And I have examples, for example, from, yes, please.
So just to clarify what the negative result is it saying that there cannot exist a model which is good at both, or it's computationally hard to find one?
No, there isn't. So this is a statistical result. We also have computational results that are even stronger. Let me get to explaining why, but also I want to say that this applies to a physician. So when people think, okay, this algorithmic fairness shows all these problems with algorithms, it doesn't show problems with algorithms, or it does show problems with algorithms. It doesn't matter if a digital computer calculates it or the mind of a physician calculates it. So these issues apply. So a physician will also, if you look at the predictions of a physician, they're either going to be calibrated or they're going to satisfy these equal errors. Yes?
Sorry, another question. This holds even if you allow for different thresholds?
Yes.
Thanks.
Yes.
Perfect.
Different thresholds will fix one, but will harm the other. Okay. So let me tell you a little bit why this is the case. What are the conditions in which it happens? The conditions is when there is some inherent uncertainty. You cannot tell me for sure if it's a 0 or 1. It's going to happen or not. If you can tell me for sure, if it's simple enough, then there are no errors at all, and everything is great. The other simple case is when the base rates are the same. There is the same prevalence of the two events in the two communities, then you can get both. But in any other case, even if you knew the best predictor, P star, using it would create gaps between false positives and false negatives. So in other words, this is not really a notion of accuracy. It just sounds like a notion of accuracy. So what would equalize odd mean for mammograms? It will mean that we're going to send many more men to mammograms, many more patients in their 20s to get mammograms, if we want to force this kind of equality. Similar phenomena in Noah's list, the list of which patients we're calling. If we want the people that we call, and in fact this is one way to sneak in some preferential treatment, is by forcing that, and it looks like you're doing accuracy. It doesn't mean that it's a bad definition. It just means that probably it's not the right definition in this context, or perhaps arguably not the right definition in this context. Let me use it quickly to talk about the value of definitions. Defining equalized odds and calibration exposed an inherent trade-off. We now know that these two things cannot happen together. We know that we have a value judgment, and we had the discussion already here, what are our values? And we'll have a different discussion perhaps when we talk about who we give bail to and who we don't give bail to. This trade-off applies to humans as much as algorithms, as digital computations. And now we can argue which is best, which is better than arguing about a system. Arguing about definitions really is arguing about the values. It gives us the question of whether there are a third notion that will give us a new trade-off, and perhaps I'll get to it. So it instigated a lot of research and gave a lot of other questions that are natural. How does the quality of the data, and we talked a little bit about it, perhaps getting other features can assist, downstream impact and others. Yes?
So maybe you'll get to this and I'm jumping to that. So when you invoked something earlier about aspects of game theory and some of these decisions and trade-offs, are you going to define this as some type of Pareto optimality? Are you going to give like a payoff matrix?
Once there are competing things, you can optimize them in different way. I'm going to actually do an optimization that's qualitative. I'm going to give you a completely third definition. Okay. So, let me jump on that, although it's a fun example, but I'm going to jump. It shows that protection to an entire population is insufficient unless you protect relevant subgroups. So let's talk about groups and individuals. The definitions that we showed here are definitions that are for several separate groups, defined by gender, for example. There are definitions of fairness that are based on, for individuals, ask something for individuals. This is one contribution of the theory of computing community. This is very intuitive but very weak, very easy to abuse. This is very refined but requires this notion of who is similar to whom. Actually, this is very relevant to healthcare because in healthcare, there are things that try to identify who is equal to whom. And in some sense, this would tell us that you need to treat similar patients similarly. But I won't talk about that. I'll talk a little bit about this notion of multi-group fairness that is kind of a trade-off in between, where we ask to have some notion of protection, not to a few disjoint sets, but for many, many arbitrarily intersecting sets. And perhaps, okay. So let's look again at this in 5 minutes. I'll do my best. I have good connections with the chair. Okay, so what do individual probabilities mean? Things are not repeatable. We already said I'm going to leave the next 10 years one. Debated within statistics. Let's look at an example from healthcare. I go to the physician, tells me that my probability is 4% of something, heart attack in the next 10 years. Why is it the case? There was a study of people like you, and people like you have 4% probability. These probabilities over sets are well defined. But I go home, and now I have access to my favorite chat, And it shows me a different study where people like me have 10% probability. And perhaps even I find another study with 4%. Does it mean that I should feel very confident about the 4%? Or perhaps this 4% is because of people like me, and so my probability is higher. And even data about probabilities that I'm not part of, sets I'm not part of it, could affect my probability. So the question of which group I'm affiliated with is extremely important from the point of view of fairness. And for example, in healthcare, there's been a movement to use other features rather than race in medical diagnosis. So it's exactly about that. Which group are we associating to you to? And the thing is that each one of us is part of a multitude of groups. So calibration asks for predictions to mean what they say when we only look at a particular group. And what multicalibration, this notion that we introduced to strengthen calibration, ask is that this to be calibrated on many, many possible affiliations, on many, many possible subgroups. So I want prediction. I want to go to the physician and not to hear of a particular study. I want my predictions to be consistent with a very, very large collection of studies. And which collection? Every set that I can identify computationally, I want to be calibrated for. This gives us a computational perspective on the meaning of probabilities. And this is almost going to be my last thing. What do I mean by computational perspective on the meaning of probabilities? When I tell you, okay, you have 10% of heart attacks in the next 10 years, 4%, not clear what it means. If you have these probabilities, if probabilities are coming from a multi-calibrated predictor, what it means is that when I watch the world, when I look at patients, and I look at these probabilities, and then I look at what happened eventually, then the world is indistinguishable from a different world. And in this different world, this probability really governs the world. So in our world, perhaps probabilities don't govern anything. But I'm giving you a generative model. I'm giving you a scientific hypothesis of how the world works that you're not going to be able to distinguish or to refute unless you're much stronger computationally. So this is a notion that has been introduced. It is a particular answer to this balance versus or equalize odd versus calibration. I won't explain why. And I just want to finish as not to, okay. This has been used in, this is from Noah's talk. I just want to say that the way they've used it is very, very limited. They looked at combinations of 5 variables. You could efficiently look at combination of 5 variables, not only these 5 variables, but variables that contain also medical things and others. So you can look at a much bigger, so not 2 to the 5 or whatever it was. You can look at things that have exponential number of sets and be calibrated for all of them and get it efficiently. It was used in this COVID example. And essentially what this gives is a different approach to learning. Instead of learning by first deciding on something we want to optimize, like optimize L2 errors or L2 loss, I'm going to learn something that's going to be good for a very large potential optimization in the future. And it kind of tells us it is an approach. It's not the answer, but it is an approach to fairness for predictors. It says that fairness for predictors means that you need to be equally accurate on a very, very large collection of subgroups, on everything that you can put your hands on ahead of time. And then you can design the actions the way you want. And this gives us a lot of very strong robustness properties. It gives us things that minimize loss not only overall, but minimize loss for a very large collection of subpopulations. It gives us only predictors, which mean that you don't need to, if you worry about L2 losses, that's fine. But if in real time you find a different loss to care about because this loss corresponds to a new medical intervention that you didn't know about when you did the study, it will be still fine. And universal adaptability means you do a research in Stanford hospital and then you use it in Baltimore. If the study produced a multicalibrated predictor, it could, under some conditions, apply to all of these other hospitals simultaneously. I didn't get a lot of time to explain all of these things, but I hope that I did talk about some of the basic challenges of fairness, and I'm happy to talk offline. And if the chair, I'll point you now, I can answer perhaps a question or two. Yes?
You didn't mention the economic angle, right? Because when you try to do all the things, there's a resource problem. Is that taken into account explicitly in the fairness?
Yeah, so these notions are relevant also for things with constraints. Absolutely, you can use these multi-calibrated predictors. Essentially, as I said, it kind of separates the act of learning. In the learning, I want to learn as much as I can about my data set. And then in application, I can do various things, including decide who gets vaccinations, and which is a resource that's limited. So yeah, these probabilities.
Talk about it.
And yeah, we're going to have a wonderful. So essentially, you can think about these probabilities as if they are the truth in some way, and then do whatever you want to do with these probabilities. Apply whatever moral judgment you want to do with those probabilities. Yes?
So you mentioned a multitude of affiliations can be very, very large, so a large number of groups, but still finite, right? But can you think of it as infinite partitions? Because if you could think of a continuous measurement, so for example, a bit rate or something like that, maybe when you split a training set, right, you can just split it to a finite number of subgroups.
Right.
But if you have theoretically now an infinite number of samples, can you have an infinite also number of subgroups?
Right. So most of our literature talks about finite number of things and exponential but finite. So for example, all the decision trees of logarithmic depth on these 40,000 attributes that Clalit has. You can say that, okay, that you look at measurements as being real, and we have some notions of calibration that actually apply to real values, but it requires a bit more thought. So it's not completely out of the blue, but in reality, eventually, all of these measurements are written in bits on your. So yeah. Okay, last question.
So when you talk about multi-calibration, do you run into questions of how to represent disagreement of evidence?
So that's the amazing thing about multi-calibration. Although we are asking for accuracy for exponential number of groups that are arbitrarily intersecting, you can get it, and actually you can get it in a way that you take any predictor you start with, learn it whatever way you want. You can start correcting a few groups, and after not too many steps, you're going to get into something that's good for all the groups. So you don't get a situation where you correct one group, or perhaps for one group, yes, you'll correct it, you make cause harm, but then you'll correct another, and after a few steps, it will turn out that you correct all of those. This efficiently kind of post-processing is what makes it a very very appealing. I know that it's used in many actual high-tech companies implicitly because it's very easy. Because I don't tell you, forget about everything you learned about creating predictors. I tell you, okay, create the best predictor that you can, and then I'm going to show you a way to make it even better. And at the end, it's also going to be multi-calibrated. So there are no, although there are exponential number of sets, this requirement of calibration is consistent. And with that, I think we'll go for a break.
Are you gonna, can I ask you questions about multi-calibration?
Yes,
Asking,
So this notion that you
I
can
didn't quite think straight.
yes.
It's because